Hold something in your hand tonight and let it go, and it falls. It is the most ordinary thing in the world. It happens so reliably, so utterly without exception, that we do not even see it as an event. A cup slips from your fingers and drops to the floor. Rain comes down. Leaves come down. A stone tossed into the air rises, slows, turns and returns. Everything, always, without a single exception in the whole of human experience, comes down. And because it is so ordinary, almost nobody for most of human history thought it was strange. It was simply what things did. Heavy things fall. That is their nature. What else would they do? But it is strange. It is one of the strangest things there is. Because something is reaching out and pulling that cup toward the floor, silently, invisibly, through empty air, without touching it. Something reaches across the emptiness between the Earth and the Moon, 250,000 miles of nothing at all, and holds the Moon in its circle. Something reaches out across 150 million kilometers of vacuum and holds this entire world and every one of us on it swinging around the sun, and it never rests and never weakens and never asks anything. And it has been doing this for 4.5 billion years without a single day off. We call it gravity. It is the weakest of all the fundamental forces, so feeble that you can defeat the pull of an entire planet by lifting a coffee cup off a table with the muscles of your arm. And yet it is the force that built everything. It gathered the dust of dead stars into new stars. It assembled the planets. It holds the galaxies together and swings them around one another across distances that light takes millions of years to cross. It is the architect of the whole visible universe, and it works by a means that nobody understood for nearly the whole of human history, and that we are even now still not entirely finished explaining. Sit with that oddity for a moment, because it is one of the great puzzles about gravity, and we will come back to it. It really is astonishingly weak. A small magnet, a thing you could hold between two fingers, can lift a paperclip off a table, and in doing so, it defeats the gravitational pull of the entire Earth, all 6,000 billion tons of it. Every time you stand up out of a chair, the muscles in your legs overpower the gravity of a whole planet, and yet gravity wins in the end, everywhere, on every scale that matters. Why? Because it has two advantages that nothing else has. It never cancels out and it never stops. The other forces do cancel. Electric charges come in two kinds, positive and negative, and they attract each other and clump together and neutralize, so that almost everything in the universe at any decent size is electrically balanced and inert. But gravity has no opposite. There is no negative mass, nothing that repels. Every scrap of matter in existence pulls on every other scrap, and it all adds up, always in the same direction, forever. So it is feeble at the scale of a paperclip and utterly dominant at the scale of a planet and completely in charge at the scale of a galaxy. It is the patient force. It does not win any single contest. It simply never loses and never stops, and it has all the time in the world. Tonight, and over the nights that follow, we are going to tell the story of how we came to understand it. It is one of the longest stories in all of science, running from the ancient world right up to the present decade, and it contains at least two of the greatest ideas any human being has ever had. It is a story about looking at the most ordinary thing in the world, the falling of a stone, and slowly, over 2,000 years, realizing that it is the same thing that moves the stars. But before we begin, let me ask you something, gently. If these quiet journeys through the great stories of our world help you set down the weight of your day and drift toward rest, then please take just a moment to subscribe. It is one small tap, but it means the next of these will find its way back to you on some future restless night. And it helps, more than you might imagine, to keep these stories being made, for you and for all the others out there in the dark tonight looking for a little peace. So if you would subscribe and travel on with me, night after night, through the great slow stories of how we came to understand our world. And I would love to know, from wherever you happen to be resting tonight, in whatever quiet corner of the world is holding you, where you are listening from, and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there together, all of us drifting off beneath the same turning sky. And now, let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me all the way back to the ancient world, to the very beginning, where the story starts with a question so simple that it took 2,000 years to answer properly. Why do things fall? Let us begin with the answer that satisfied the world for nearly 2 millennia, because it was a good answer and a beautiful one, and it was completely wrong. In the ancient Greek world, there lived a philosopher of such extraordinary range and ability that his writings would dominate European thought for the better part of 2,000 years. He wrote about logic, about biology, about poetry, about politics, about the soul, about very nearly everything, and much of it was brilliant, and he wrote about why things fall. His answer went something like this. Everything in the world below the moon, he said, is made of 4 elements: earth, water, air, and fire. And each of these elements has a natural place where it belongs, where it wants to be. Earth belongs at the center, the lowest place. Water belongs above it. Air above that. Fire highest of all. And every object, made mostly of one element or another, naturally seeks to return to its proper place. So a stone falls because it is made mostly of earth, and earth belongs at the center, and the stone is simply going home. A flame rises because fire belongs above. A bubble of air rises through water for the same reason. Nothing is pulling anything. Things move toward where they belong, the way a person walks home at the end of a long day. Rest with that a moment, because I think it deserves some sympathy rather than mockery. It is not a stupid idea. It explains a great deal of what you actually see. Stones do fall, flames do rise, bubbles do go up through water. It fits the evidence of ordinary life remarkably well. And it has a certain poetry to it, this picture of a universe in which everything has a proper home and is quietly trying to get there. For 2,000 years, thoughtful people found it entirely convincing, and it takes nothing away from us to see why. But it carried with it a second idea, and this second idea was the truly consequential one, and it would take even longer to overturn. Because if earth, water, air, and fire all belong below the moon, and if everything down here is restless, changing, decaying, falling, then what about everything above? The moon, the sun, the planets, the stars. They do not fall, they do not decay. They circle endlessly in perfect and unchanging patterns, and they have done so for as long as anyone had ever recorded. So they must, he reasoned, be made of something else entirely. A fifth element, a heavenly substance, perfect and unchanging and eternal, whose natural motion is not falling but circling. And the heavens must therefore be a completely separate realm from the earth, governed by completely different laws, made of completely different stuff. That was the picture. 2 worlds. Down here, the messy realm of change and decay and falling. Up there, the perfect realm of eternal circles, and a hard boundary between them. At the moon, across which nothing passed and nothing was shared. And I want you to feel how deep and how reasonable that division seemed, because everything that follows in this story is, in one way or another, the slow dismantling of it. Look up at the night sky, really look. The stars turn overhead in perfect order, night after night, year after year, unchanging within any human lifetime. Now look at the world around you. Things break, things rot, things fall down, nothing lasts. Of course, those are 2 different realms. Of course, the heavens are made of something purer. What could a falling stone possibly have in common with the moon? Everything, as it turns out. But it would be a very long time before anyone could show it. For centuries, that was the settled account, and it hardened into something close to doctrine. It was taught in every university. It was woven together with philosophy and theology into a single grand picture of the cosmos, and to question one part of it was to unsettle the whole, which is one of the reasons it lasted so long. It was not merely a theory about falling stones, it was the architecture of the world. And it is worth naming why that mattered so much, because it explains a great deal of what follows. In that picture, the Earth sat still at the center of everything, and around it turned a series of vast crystalline spheres, carrying the moon and the sun and the planets and finally the fixed stars. And beyond the outermost sphere lay the realm of the divine. It was a cosmos, with a shape and a purpose and a place for everything, including us. We were at the center, at the bottom, in the realm of change and decay, with perfection arranged in tiers above our heads. You can see why people loved it. It was orderly and meaningful, and it told you where you stood. Every part of it fitted every other part, and you can also see why questioning any single piece felt so dangerous, because the pieces held each other up. Say that the moon is a rocky world with mountains, and you have not merely corrected a detail. You have knocked a stone out of the foundation of a cathedral. But there were problems in it, and thoughtful people noticed them. One of them had nothing to do with falling at all, but with throwing, and it had bothered people for centuries. If things only move when something is actively moving them, then what keeps an arrow flying after it has left the bow? The bowstring pushed it, certainly, but the string is behind it now, no longer touching it, and yet the arrow sails on across the field. What is pushing it? The old answer was that the air did it, closing in behind the arrow and shoving it forward, which nobody was ever really happy with, since air is also the thing slowing the arrow down, and it seemed a great deal to ask of it to do both jobs at once. Thinkers in the medieval world, in the Islamic world, and later in Europe, chewed on this problem for centuries, and some of them came remarkably close to the right answer, proposing that the thrower gives the object some quality of motion that it then carries with it, and gradually uses up. That is not far off, and it points at something the ancients had missed entirely, which is that motion itself does not need explaining. Only changes in motion do. A thing left alone simply keeps doing what it was doing. That insight would have to wait to be stated properly, but you can see people reaching for it. In the centuries before, circling around it, not quite able to say it. Here is the most famous problem, though, and it is so simple that a child can follow it. According to the old picture, heavier objects fall faster than lighter ones in proportion to their weight. A stone twice as heavy should fall twice as quickly, because it has twice as much earth in it, twice as much urge to reach the center. Now imagine, said a clever objector, that you take a heavy stone and a light stone and you tie them together with a piece of string and drop them. What should happen? Well, on the one hand, the light stone falls more slowly, so it ought to hold the heavy one back, and the pair should fall at a speed somewhere between the two. But on the other hand, tied together, they are now a single object, heavier than either one alone, and so the pair ought to fall faster than the heavy stone by itself. Both conclusions follow from the same rule, and they contradict each other, which means the rule cannot be right. Rest there a moment and enjoy the elegance of that, because it is one of the loveliest arguments in the history of thought. No equipment, no experiment, no expense, just a piece of string, imagined, and a rule that falls apart in your hands when you think it through carefully. This is what philosophers call a thought experiment, and it is one of the great tools of the human mind. And this particular one is more than 400 years old and has never lost a bit of its force. That argument, in its most famous form, comes to us from a man in northern Italy in the late 1500s and early 1600s, who did more than anyone else to break the old picture apart. He is one of the towering figures in the history of science, and he is remembered today for many things, but the heart of his contribution was a change in method that seems obvious now and was revolutionary then. He measured. That is the whole of it, and it changed everything. Rather than reasoning about what ought to happen from first principles, in the manner of the philosophers, he went and found out what actually happens. He built apparatus, he timed things. He wrote down numbers and compared them, and looked for patterns in them. It sounds so ordinary now that it is hard to feel the shock of it. But for 2,000 years, the way to settle a question about nature had been to think carefully and consult the great authorities. He went and rolled balls down a ramp instead, and wrote down how long they took, and trusted the numbers over anybody's opinion, including his own. There is a famous story about him dropping 2 balls of different weights from the Leaning Tower of Pisa in front of a crowd to show that they landed together. It probably never happened, or at least not in the way the story tells it, and that is fine. The story survives because it captures something true about him, even if the details are invented. What he actually did was cleverer, and it solved a problem that had defeated everyone before him. The problem is this: falling is too fast. Drop something from a height you can reach, and the whole event is over in under a second. With the timekeeping available in his day, no clock, no stopwatch, nothing capable of measuring fractions of a second, it was simply impossible to study a fall directly. The thing happens and it is finished before you can measure anything about it. So he slowed it down. He took a long straight plank and cut a smooth groove down the length of it and propped one end up to make a gentle ramp and rolled a bronze ball down it. A ball rolling down a shallow slope is doing the same thing as a falling ball, in essence moving under the same pull, but stretched out over many seconds instead of a fraction of one. Slow enough to measure. And measure he did over and over with real care. He marked distances along the groove, and for timing, since he had no clock good enough, he used water, letting it run steadily from a vessel into a cup during each roll, and then weighing the water afterward. More water meant more time. It sounds primitive, and it was also accurate enough to reveal something that nobody had ever seen. There is a lovely detail in his account of it too. He lined the groove with smooth parchment to reduce the friction, and he described polishing the bronze ball until it was perfectly round and smooth. And he wrote that he repeated the experiment a full 100 times at various slopes and various distances until the results agreed with each other so closely that the differences were negligible. 100 times. Sit with that for a moment. This is what the beginning of modern science actually looked like. Not a flash of insight in a bathtub, not an apple falling on a head, but a man in a workshop, rolling the same polished ball down the same parchment-lined groove, over and over, day after day, weighing cups of water, writing down numbers and doing it again to be sure. It is patient, unglamorous, almost tedious work. And it produced a truth that had eluded the greatest minds of 2,000 years, because none of them had thought to simply go and check. He found that the distance a rolling ball covers does not grow steadily with time. It grows with the square of the time. In the second unit of time, it covers 3 times as much ground as in the first. In the third, 5 times. In the fourth, 7. The odd numbers, 1, 3, 5, 7, over and over, in every trial, at every angle of the ramp. That regularity is the signature of steady acceleration. It means the ball is not simply moving, but speeding up, and speeding up by exactly the same amount in every equal interval of time, forever. Falling is not a state. It is a constant, unrelenting increase in speed. And here is the part that mattered most, the thing that shattered the old picture. He varied the weight of the balls. A heavy bronze ball and a lighter one rolled down the same ramp from the same height. They arrived together, not approximately, not roughly. Together, within the precision of anything he could measure. The weight made no difference at all. A heavy object and a light object released together fall in exactly the same way. Rest there a moment and let that sink in, because it is one of the most surprising facts in all of physics, and familiarity has worn away how strange it truly is. Everything falls at the same rate. A cannonball and a pebble, a boulder and a grain of sand, an elephant and a mouse. Drop any 2 things together and they land together, regardless of what they weigh or what they are made of. Your everyday experience seems to argue against this, of course. Drop a feather and a coin, and the coin wins easily. But that is not gravity. That is air. Catching the feather and holding it back. Take the air away, and the feather and the coin fall side by side and land at exactly the same moment. This has been done in vacuum chambers many times, and most beautifully of all on the surface of the moon, where an astronaut dropped a hammer and a falcon feather in front of a television camera and let the whole world watch them land together in the dust. I love that moment more than almost any other in the history of science demonstrations. 3.5 centuries after a man in Italy worked this out with a wooden plank and a bucket of water, a human being standing on another world held out a hammer in one hand and a feather in the other, said that he would try a little experiment here, and let go. And the 2 of them drifted down together at the same rate, in perfect silence. Hand touched the grey dust at the same instant, and he said, well, that proves the man was right. It is a small thing, a few seconds of grainy footage. But somebody had to carry a feather all the way to the moon in order to do it, on purpose, because they thought it was worth showing, and it was. But he could not have known that. He had no vacuum chamber and no moon to stand on. He had a wooden plank, a bronze ball, and a bucket of water, and out of those he pulled a truth about the universe that contradicted 2,000 years of authority. And it is worth pausing on what that truth actually implies, because it is deeply odd when you sit with it. A heavy object is harder to move, Push a boulder and a pebble along a smooth floor with the same effort, and the pebble shoots away while the boulder barely stirs. Heavy things resist being accelerated. That is what heaviness means, in one sense. And yet gravity also pulls harder on the boulder than on the pebble. That is what heaviness means in another sense. So when you drop them, two things are happening at once. Gravity pulls harder on the heavy object, but the heavy object also resists that pull more strongly, in exactly the same proportion. The two effects cancel out perfectly, precisely, exactly, to every decimal place anyone has ever managed to measure. There is no obvious reason why they should. These are two entirely separate properties. One is about how strongly gravity grips a thing. The other is about how stubbornly a thing resists being pushed around. There is no reason at all for them to be the same number. And yet they are exactly always, and nobody had the faintest idea why. Let me put it another way, because it is worth being clear about how strange this is. Imagine you discovered that in every person on Earth, the length of their arm was exactly equal, in some appropriate units, to the volume of their voice. Every single person, without exception, measured to extraordinary precision. You would not say, "How nice." You would say, "Something is going on here." Those two things have nothing to do with each other. There must be some hidden reason. That is the situation with gravity. The property that determines how hard gravity pulls on an object and the property that determines how hard the object is to accelerate are conceptually unrelated, and yet they are identical in every object that has ever been tested. Experiments have confirmed it to a staggering precision, better than 1 part in a trillion, and it holds for every material that has ever been checked. For iron and aluminium and gold and plastic and anything else anyone has thought to try. That coincidence, that suspicious and perfect equality, would sit quietly in physics for 300 years, noticed but unexplained, an oddity that everyone knew about and nobody could account for. And then at the beginning of the last century, a young man would look at it and realize that it was not a coincidence at all, but the most important clue in the whole of physics, and that it meant something extraordinary about the nature of space and time. But that is the third of our nights, and we are getting ahead of ourselves. Let us come back to our Italian, because he did one more thing that matters enormously to this story, and it was the thing that got him into so much trouble. He pointed a telescope at the sky. The instrument had been invented shortly before, in the Netherlands, mostly as a curiosity and a tool for merchants and soldiers. He heard about it, worked out the principle for himself, built a far better one than the originals, and then did the thing that changed history. He turned it upward, and what he saw broke the old universe apart. He looked at the moon, that perfect, unblemished sphere of heavenly substance, and found it covered in mountains and craters and vast dark plains. He could measure the heights of its mountains by the lengths of their shadows. It was not a polished heavenly orb at all. It was a world, a rugged, mountainous, cratered world, rather like our own. He looked at the sun and found dark blemishes on its face, spots that came and went and moved across it as it turned. The sun changed. The perfect and unchanging heavens had a blotchy, shifting face. He looked at the great planet Jupiter and found 4 small points of light beside it, and watched them night after night, and realized they were moving, circling. There were 4 moons going around Jupiter, which meant that not everything in the heavens circled the Earth. There was another center of motion out there. He looked at the Milky Way, that soft band of light across the sky, and found it resolved into countless individual stars, more stars than anyone had imagined existed. And he looked at the planet Venus and found that it goes through phases exactly as our moon does, sometimes a thin crescent, sometimes half-lit, sometimes nearly full, and crucially, it was largest when it was a crescent and smallest when it was full. That pattern is impossible if Venus circles the Earth. It is exactly what you would expect if Venus circles the Sun, sometimes passing near us on the inside of its orbit, and sometimes far away on the other side. It was, quietly, one of the most damaging observations of all. Rest a moment and try to feel what those nights must have been like for him. He was, for a short period, quite alone in a way that almost nobody has ever been. He was the only living person who knew that the moon had mountains, the only one who had seen the moons of Jupiter. He would look, and check and look again, and then go and write it all down. knowing that the sky above everyone's head was not what anyone had thought. And the deepest consequence of all of it was this: the heavens were not a separate realm of perfect, unchanging substance. The moon was a world with mountains and valleys made of rock like this one. The sun had blemishes and changed. The boundary that the ancient philosopher had drawn between the earthly and the heavenly, the whole 2,000-year-old division of the cosmos into two kinds of place governed by two kinds of law, was simply not there. Which raised, though he could not yet answer it, the most important question in this entire story. If the heavens are made of the same stuff as the earth, and if there is no dividing line, then does the same physics apply up there too? Do the same rules that govern a falling stone also govern the moon? Is whatever pulls the apple down also somehow holding the planets in their courses? He did not solve it. Nobody in his lifetime solved it. He had proved that things fall together regardless of weight. And he had proved that the heavens are made of ordinary stuff. And he had left, lying side by side, the two halves of an idea that nobody had yet joined. He suffered for the rest of it, as you may know. His support for the notion that the earth moves around the sun brought him into conflict with the authorities of his day, and he was tried and made to publicly renounce what he believed to be true, and spent his final years confined to his house, going blind, still working, still writing, dictating his last and perhaps greatest book to his students when he could no longer see the page. And that last book, written under house arrest by a man in his 70s who could not see, is the one that actually matters most for our story. It is not the famous one about the earth and the sun that got him into trouble. It is the quieter one, about motion, about how things fall and roll and fly, gathering together all the work of his lifetime, with the ramps and the balls. He had it smuggled out of Italy and published abroad, because he could not publish it at home. And it became the foundation on which the next generation would build. There is something quietly defiant in that and quietly hopeful. Forbidden to teach, watched, forced to recant, going blind, he simply turned to the part of his work that nobody had thought to forbid, and wrote the book that would outlast every one of his judges. Not one of the men who tried him is remembered by name outside of specialist history. His book is still in print. Rest there for a moment, gently, because it is a hard part of a beautiful story. He did the work. He measured the falling and turned the glass upward and saw what nobody had ever seen, and he was made to say aloud that he had been wrong. He died under house arrest, and he was right. Everything he had been forced to renounce was true and is taught to schoolchildren everywhere today as ordinary, uncontroversial fact. The universe does not care who wins an argument. It simply goes on being what it is, patiently, until we are ready. And so we arrive at the end of tonight with the pieces laid out and unassembled. We know now, as of the point our story has reached, that all objects fall in the same way regardless of weight, and that falling means steady acceleration, and that the numbers describing it are beautifully regular. We know that the heavens are made of the same ordinary material as the earth, that the moon is a world of rock and mountains, and that the ancient boundary between the earthly and the celestial does not exist. What we do not have is any idea what gravity actually is. Nobody has yet said that anything is pulling. Nobody has proposed a force at all. The falling of stones and the wheeling of the planets are still two separate subjects, studied by different people for different reasons, with no known connection between them beyond a growing suspicion that there ought to be one. That connection, the greatest single leap in the history of science, when one man realized that the falling of an apple and the circling of the moon are precisely the same event, is where we will go next time. But not tonight. Tonight, let the story rest here, in the years just before the Great Unification, with the ramps and the bronze balls put away, and the telescope on its stand pointing quietly at a sky that nobody yet understood, and the two halves of the answer lying near each other in the dark, waiting for someone to see that they fit. So let your breathing slow, and let the ancient philosopher with his four elements, and the string tied between two stones, and the water running quietly into a cup, and the old man dictating his last book to his students in a room he was not allowed to leave, all grow soft and dim and far away. It was all so very long ago. They have all long since laid down their instruments and gone to their rest, having handed the question on, as we all do, to the ones who came after. There is nothing here you need to hold or carry tonight. It is only a story, a quiet story about people looking very carefully at ordinary things and slowly noticing how strange they are, told to carry you gently down into sleep. And I would leave you with one small thought, if you are still with me, because it is the loveliest thing about this particular story, and it cost nothing to notice. Every single thing in this episode was discovered by paying attention to something completely ordinary. Not by traveling anywhere, not by building anything enormous. A stone falling, a ball rolling down a plank, two objects landing at the same time. These are things that were happening constantly, everywhere, in front of everyone, for the whole of human history, and almost nobody looked at them properly. The universe was not hiding this, it was doing it openly, in every dropped cup and every falling leaf, in front of every person who ever lived, for 100,000 years, waiting for somebody to be curious enough to measure it. That is worth remembering on an ordinary evening in an ordinary room. The extraordinary things are often not far away. They are usually right here doing what they always do, waiting to be noticed. And gravity is holding you right now as it happens, and has held you every moment of your life without once faltering. It is holding you in your bed and holding the air above you, and holding this whole turning world together beneath you. And it will not stop while you sleep. And it has never stopped, not once, in 4.5 billion years. Of all the forces in the universe, it is the one that never lets go. Sleep now, warm and safe and held, on a solid world that is exactly where it should be. The story will still be here tomorrow and the night after, and we have all the time in the world to follow it, gently together, from the falling of a stone to the turning of the stars. Last time we left the two halves of the answer lying near each other in the dark. We had followed the story from the ancient world, from the beautiful and entirely wrong picture of 4 elements seeking their natural homes, through the long centuries in which the heavens and the earth were held to be 2 separate realms, made of different stuff and governed by different laws. We had watched a man in northern Italy roll bronze balls down a wooden plank 100 times and discover that everything falls at the same rate, whatever it weighs. And we had watched him turn a telescope on the sky and find mountains on the moon and spots on the sun, and so quietly demolish the boundary between the earthly and the celestial. So the pieces were there, the falling of stones, now measured and understood, and the heavens, now known to be made of ordinary stuff, and nobody had yet joined them. Nobody had yet said the sentence that would unite them, because the sentence sounds, at first hearing, completely absurd. Tonight, somebody says it. Tonight we come to what is arguably the single greatest leap in the history of science. The moment one man realized that the falling of an apple and the circling of the moon are not 2 phenomena at all, but exactly the same thing, happening in exactly the same way for exactly the same reason, and that from that one idea, written down as a piece of mathematics that fits comfortably on a single line, you can derive the motion of very nearly everything in the sky. But before we begin, let me ask you again gently, as I will each night, if these quiet journeys through the great stories of our world help you set down your day and find your way toward rest, then please take just a moment to subscribe. It is one small tap, but it means the next of these will find its way back to you on some future restless night, and it helps more than you might know to keep these stories being made, for you and for everyone else out there in the dark tonight. So if you would, subscribe and stay with me, night after night, as we wander on together through the great slow stories of how our world came to be understood. And tell me, if you will, from wherever you are resting tonight, where you are listening from, and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there, all of us drifting off together beneath the same turning sky. And now let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me back to where we left the story, to England, in the years of a great plague, and to a young man sent home from his university, with nothing much to do. Let us begin with the closing of the colleges. In the middle 1660s, plague swept through England, and the universities shut their doors and sent everyone home. Among those sent away was a young man in his early 20s, recently graduated, not yet distinguished, who returned to the small farmhouse in the countryside where he had grown up. He would be there on and off for the better part of 2 years. He was a strange and difficult person by every account that has come down to us. Solitary, secretive, prone to holding grudges for decades, uninterested in company, and largely uninterested in publishing what he discovered, which is one of the reasons the world had to wait so long for so much of it. He would work through the night, forget to eat, forget to sleep, and emerge with something that had moved the boundaries of human knowledge and then simply put it in a drawer. And in those 2 plague years, alone in the countryside with no lectures to attend and no one to talk to, he did more original thinking than most people manage in a lifetime. He worked out the mathematics of change, what we now call calculus, which is the language in which nearly all of physics is still written. He took a prism and passed sunlight through it and discovered that white light is not pure but is made of all the colors mixed together. And he began to think about gravity. He referred to that period, much later in his life, as the prime of his age for invention, and said that in those years he minded mathematics and philosophy more than at any time since. He was 23. And it was during that period, according to the story he told in his old age to several people, that he sat in the garden of that farmhouse and watched an apple fall. Now, the apple. Let us take a moment with the apple, because it is one of the most famous images in the history of science, and it is almost universally misunderstood. The story, as usually told, has the apple falling on his head and knocking the idea of gravity into him. That never happened, and he never claimed it did. What he actually described was simply sitting in a contemplative mood when the fall of an apple set him thinking. There was no blow to the head, and there was no sudden discovery of gravity, because gravity did not need discovering. Everybody already knew that things fall. That was not the question. The question was something else entirely, and it is the real content of the story. He was sitting there, watching the apple come down, and he happened to look up, and the moon was in the sky, as it often is in daylight, a pale disk up above the trees. And he asked himself the question that nobody had ever quite asked in that form. Why does the apple fall and the moon does not? That is the whole thing. That is the seed of everything. And notice how good a question it is. Under the old picture, it barely arises because the apple is earthly and the moon is celestial and they obey different laws, and of course they behave differently. But the old picture was broken now. The moon was a world, made of rock with mountains. So if the moon is made of ordinary stuff and ordinary stuff falls, then why in heaven's name is the moon not falling? And then came the leap, the extraordinary, beautiful, world-changing leap. It is falling. The moon is falling, constantly. It has been falling for 4.5 billion years, and it has never once stopped falling. It simply never arrives, because it is also moving sideways, fast. And the 2 things together carry it around and around forever. Let me give you a picture of it, because he gave one himself, and it is the clearest explanation ever offered of an orbit. Imagine standing on a very high mountain with a cannon. You fire the cannon horizontally, and the ball flies out and arcs down and lands some distance away. Load more powder and fire again, and it goes further before it lands. More powder still, further still. Each time the ball is falling toward the earth exactly as before, but it is also moving sideways so quickly that it covers a great deal of ground on the way down. Now keep increasing the powder. There comes a point, and this is the beautiful part, where the ball is moving sideways so fast that as it falls toward the earth, the surface of the earth curves away beneath it at exactly the same rate. It falls, and the ground drops away, and it falls, and the ground drops away, and it never gets any closer. It goes all the way around the world and comes up behind you. That is an orbit. That is all an orbit has ever been. Not floating, not weightlessness in the sense of gravity being absent, falling endlessly and missing the ground because you are going sideways fast enough. The moon is a cannonball that never lands. It is falling toward the earth every second, pulled by the same thing that pulls the apple, and it has simply been missing us for 4.5 billion years. Rest there a moment and let that settle, because it is one of the loveliest ideas in all of science, and it repays a little quiet. Everything in orbit is falling. The space station overhead is falling. The astronauts inside it are not floating because they have escaped gravity, since gravity up there is nearly as strong as it is in your bedroom. They are floating because they and their spacecraft are falling together at the same rate, exactly as the hammer and the feather fell together on the moon. The whole solar system is an enormous, patient, endless act of falling that never arrives anywhere. And notice how neatly that ties back to the discovery of the previous night. Everything falls at the same rate, whatever it weighs, which is exactly why an astronaut and their spacecraft, wildly different in mass, fall together so perfectly that the astronaut appears to float inside it. The two of them are simply on the same trajectory, side by side, the way the hammer and the feather were. Weightlessness is not the absence of gravity. It is the experience of falling with everything around you. You have felt a small version of it yourself. That lift in the stomach as a lift begins to descend, or the top of a hill in a car, or the first drop on a fairground ride. That is your body noticing that for a moment the floor is not pushing up on you as hard as usual. Take that feeling and extend it forever, and you have an orbit. Astronauts are not floating. They are falling permanently around the world 16 times a day and missing every time. But an idea is not science until you check it. And this is where the young man in the farmhouse did the thing that made him one of the greatest scientists who ever lived. He did the arithmetic. If the same pull reaches from the Earth to the moon, he reasoned, it must weaken with distance. So he asked by how much, and he had a good guess available because a rule of that shape had been floating around among the natural philosophers of the age. The pull should weaken with the square of the distance. Go twice as far away and it becomes a quarter as strong. 3 times as far, a ninth. 10 times, a hundredth. There is a reason for that shape, and it is worth a moment because it is so satisfying. Think of the influence spreading out from the Earth in all directions, like light from a lamp. As it goes further out, that same influence has to cover the surface of a bigger and bigger sphere. And the surface area of a sphere grows with the square of its radius. So the same amount of influence, spread over 4 times the area, is 4 times more thinly spread. It falls off with the square of the distance, not because anybody decided it should, but because that is simply what happens to anything spreading outward in 3 dimensions. So he tested it. He knew roughly how fast things fall at the Earth's surface. He knew roughly how far away the moon was, about 60 times the radius of the Earth, so the pull out there should be about 3,600 times weaker, and from that he could calculate how fast the moon should be falling and therefore how long it should take to go around. And the answer came out close to right. Not perfect, because the figures available to him for the size of the Earth were not very good, but close. Close enough to see that the idea was working. The same rule, the same force, the same mathematics, describing an apple in a garden and the moon in the sky. The 2 realms were one. There was no dividing line at the moon. There was no separate celestial physics. There was one universe made of one kind of stuff, obeying one set of laws from the apple in the grass all the way out to the furthest thing anyone could see. And then he put it in a drawer for 20 years, which is such a perfectly characteristic thing for him to have done that it almost makes me laugh. He had, in his early 20s, unified the heavens and the earth, and he simply did not get around to telling anybody, and went off to work on other things, including a great deal of alchemy and theology that occupied far more of his life than physics ever did. What finally got it out of him was a visit, some 20 years later, from a younger astronomer, a genial and generous man who is one of the quiet heroes of this story. There was an argument going on in London among the natural philosophers of the day. They had all more or less guessed at the inverse square rule. What none of them could do was prove what it implied. If the pull between the sun and a planet follows that rule, what shape must the planet's path be? Everyone suspected the answer, since the shapes of the planetary orbits had been worked out from observation decades earlier, but nobody could derive it. So the visitor traveled to Cambridge and put the question to the reclusive professor. If the force follows an inverse square law, what curve would a planet describe? And the answer came back immediately, without hesitation. An ellipse. The visitor, startled, asked how he knew. "Because I have calculated it," said the professor. He was asked to produce the calculation and could not find it, and said he would work it out again and send it on. And what came back some months later was not a scrap of working but a small treatise. And the visitor read it and understood what he was holding, and set about with enormous patience and at his own personal expense, persuading this difficult man to expand it into a proper book, and then seeing that book through publication. It took 3 years of obsessive work, and what emerged in the late 1680s is generally regarded as the most important scientific book ever written. Rest a moment there on the visitor rather than the professor, because he deserves it. The world got that book because one generous person went to Cambridge to ask a question, recognized what he had found, spent 3 years coaxing and encouraging and editing, and then paid for the printing out of his own pocket when the learned society that should have funded it had spent its money on something else. Genius is not enough on its own. Somebody usually has to go and knock on the door. And what was in that book? 3 laws of motion. First, describing how anything moves under any influence. That a thing left alone keeps doing what it was doing, moving in a straight line at a steady speed forever until something acts on it. That when something does act on it, the resulting change in motion depends on the strength of the push and the mass of the object. And that every push comes with an equal push in the opposite direction, so that the earth pulls the apple down and the apple pulls the earth up by an amount so tiny that nobody will ever measure it. And then the great one, the law of universal gravitation. Every object in the universe attracts every other object. The strength of the attraction grows with the mass of each of them and weakens with the square of the distance between them. That is it, that is the whole law, and I want you to notice the word universal because it is doing enormous work there, and it was the truly radical part. Not the earth attracts things, not heavy objects seek the center. Every object attracts every other object, everywhere, always, without exception, throughout the entire universe, which means the sun pulls on the earth and the earth pulls back on the sun. The moon pulls on the oceans, which is why we have tides. Jupiter pulls on Saturn and slightly disturbs its orbit. You pull on the chair you are sitting in, and it pulls on you unmeasurably faintly. Every particle of matter in existence is in silent conversation with every other particle across any distance forever. And the tides are worth a moment on their own because they were one of the first great triumphs of the new picture, and because they had baffled everyone for as long as there had been people living by the sea. Sailors and fishermen had known for thousands of years that the tides follow the moon. Everyone could see it. The connection was obvious and completely unexplained, and more than one great thinker had gone badly wrong trying to account for it, including our Italian of the previous night, who was convinced the moon had nothing to do with it and proposed a mechanism involving the Earth's motion that was simply wrong. The new law explained it in a sentence. The moon pulls on the Earth and it pulls hardest on whatever is nearest to it. So the water on the side of the Earth facing the moon is pulled slightly more than the solid Earth beneath it and rises. And the Earth itself is pulled slightly more than the water on the far side. So the Earth moves out from under that water and it rises too. 2 bulges on opposite sides and the Earth turning underneath them, which is why most coasts have 2 high tides a day. Every tide that has ever risen on every shore in the world, every one that rose before there was anybody to see it, and every one that will rise tonight while you sleep, is the moon and the sun quietly pulling at the sea. That is what those equations are describing. It is a strange and rather beautiful thought, that the same line of mathematics that tells you where a comet will be in 76 years also tells the water when to come up the beach. One rule, one line of mathematics. And with it, you can calculate the orbits of the planets, the paths of the moons, the shape of the Earth, the timing of the tides, the flight of a cannonball, and the fall of an apple, all with the same equation. Rest there a moment and feel the scale of what had just happened. Before that book, the heavens were a mystery, described by patterns that had been fitted to observations without anybody knowing why they held. After that book, the solar system was a machine whose workings were understood and whose future could be calculated. Humanity had gone in a single volume from watching the sky to predicting it. And predict it we did. And the successes came in one after another, each more impressive than the last. The generous visitor who had made the book happen turned the new mathematics on comets. Comets had always been terrifying, unpredictable, taken for centuries as omens of disaster, appearing without warning and vanishing again. He gathered historical records of comet sightings and calculated their paths using the new law, and noticed that 3 comets recorded in different centuries had nearly identical orbits. He concluded they were the same object, coming back around on a long ellipse of about 76 years, and he predicted, publicly, that it would return in the winter of 1758. He died 16 years before that date, and on Christmas night in 1758, a German farmer with a telescope found it, exactly where it had been said it would be. And it has borne that astronomer's name ever since. Think about what that meant to people. An object that had been an omen of doom for the whole of human history turned out to be a rock on a schedule. The universe was not capricious. It kept appointments, and it is hard now to feel how frightening comets had been. They appear without warning, hang in the sky for weeks, night after night, growing and then fading, and then vanish for a lifetime or several. Every civilization that ever existed recorded them, and nearly all of them read them as warnings. The death of kings, the fall of cities, plague, war, famine. When a great comet appeared over Europe in the previous century, people fled churches in terror, and preachers wrote pamphlets about the wrath to come. A comet was the sky doing something unscheduled, and an unscheduled sky was terrifying. And then a man sat down with some old records and a piece of mathematics and said, that one will be back in the winter of 1758, and it came back in the winter of 1758, on time, as ordinary and as reliable as a train. Rest a moment with that, because something quietly enormous happened there, and it was not only about comets. A whole category of dread was taken out of the sky and replaced with a timetable. The heavens stopped being a place where things happened to us and became a place where things simply happened on schedule, whether or not anyone was watching. Some people mourned that and still do, but there is a deep comfort in it too, and I think it is worth carrying to bed. The sky is not sending you messages. It never was. It is just very large and very regular and entirely indifferent, and in its indifference there is a kind of peace. Then came the shape of the Earth. The new theory predicted that a spinning world should bulge slightly at its equator and flatten at its poles. Expeditions were sent, at great expense and considerable hardship, to measure the Earth near the equator and near the Arctic. And the Earth was flattened, exactly as predicted. And then came the greatest of them all, and it is still to my mind one of the most astonishing things anyone has ever done. By the 1840s, the planet Uranus had been known for some 60 years, and there was a problem with it. Its position never quite matched the predictions. The discrepancies were tiny, but they were persistent and growing, and nobody could explain them. 2 mathematicians, working independently, one in England and one in France, made the same audacious guess. What if the law is fine and there is simply another planet out there, further out, unknown, whose gravity is tugging on Uranus and pulling it off course? And then they did something remarkable. They worked backward. From the tiny errors in the position of Uranus, they calculated where the unknown planet must be, how heavy it must be, and where in the sky an astronomer should point a telescope to find it. The Frenchman sent his prediction to an observatory in Berlin. The astronomer there read the letter, went out that same night, pointed his telescope at the position given, and within an hour found a planet that no human being had ever seen, within 1 degree of where the mathematics had said it would be. There is a small human drama in that too, and it is rather touching. The Englishman had finished his calculation first and had tried to interest the astronomers of his own country, and had been politely ignored, partly because he was young and unknown, and partly through simple bad luck and missed appointments. His countrymen did eventually begin a search, in a leisurely sort of way, and had actually recorded the planet twice without recognizing it. Because they had no good star chart of that region, and did not notice that one of the points of light was not a star. The Berlin Observatory happened to have a brand new chart of exactly that patch of sky, freshly printed, not yet widely distributed. So when the astronomer looked, he could compare what he saw against the chart, and immediately spot the object that was not supposed to be there. It came down to that. A recent map, and someone willing to go outside and look on the same evening the letter arrived. There followed a rather undignified international squabble about who deserved the credit, which went on for years, and which history has settled by simply crediting both mathematicians, since they had done the same work independently, and both had it right. Rest there a moment and hold that, because it is one of the great moments in the history of the human mind. A planet was discovered with a pencil. Somebody sat at a desk with pen and paper and the small deviations of another world's motion, and worked out that there had to be something out there, and where it was, and how big. And then a telescope was pointed at that patch of empty sky, and there it was. That is what it looks like when a theory is truly right. It does not just explain what you have already seen. It tells you what you have not yet seen. And then you go and look, and it is there. By that point, the theory of gravity was the most triumphantly successful idea in the history of science. It had ruled for a century and a half without a single serious failure. It was, to most people, simply the truth about the universe, complete and finished. And yet, two things nagged, and it is worth ending tonight on both of them, because between them they contain the whole of what comes next. The first was a philosophical worry, and it had bothered the great man himself more than anyone. His law says that the sun reaches across 150 million kilometers of empty space and pulls on the Earth. But how? What is doing the pulling? There is nothing in between. There is no rope, no rod, no medium, nothing at all, and yet the influence somehow gets across instantly with no apparent mechanism. He was deeply uneasy about this. He called the idea that one body could act upon another at a distance, through empty space without any medium in between. So great an absurdity that he believed no competent thinker could ever accept it. Those were close to his own words. He had written the law that describes the pull, and he did not believe that the pull, as he had described it, could actually be how it works. And when pressed to explain what gravity really is, he refused. He said in a famous phrase that he framed no hypotheses. He had described what gravity does precisely and mathematically, and it worked, and that was enough. And the question of what it actually is, he left deliberately and honestly unanswered. It would stay unanswered for more than 200 years. And I want to defend that refusal for a moment, because it is sometimes read as a dodge, and it was not. It was one of the most important decisions in the history of science, and it is a large part of why the theory succeeded so completely. He could have invented a mechanism. He could have proposed invisible fluids, or swirling vortices, or tiny particles streaming between bodies and pushing them together. And plenty of his contemporaries did exactly that, and their explanations sounded satisfying and were entirely wrong and are entirely forgotten. He declined. He said, in effect, here is precisely what happens, here is the mathematics, here are the predictions, go and check them. What causes it I do not know, and I will not pretend to. That is intellectual honesty of a very high order, and it is harder than it sounds. It is uncomfortable to hold a thing that works perfectly and admit that you do not know why. The temptation to fill the gap with a story is enormous. He left the gap open and labeled it clearly, and got on with what he could actually demonstrate. And because he left it open, somebody could eventually come along and fill it properly. The second problem was much smaller and looked at first like a triviality. It concerned the innermost planet, the little one closest to the sun. Its orbit, like all orbits, is a slightly squashed ellipse, so there is a point where it comes closest to the sun. And that closest point does not stay put. It creeps around very slowly, so that the whole ellipse slowly rotates over the centuries. Most of that creeping is easily explained. The other planets tug on it, and when you add up all their pulls, you can calculate exactly how much the orbit should rotate. And when astronomers did that calculation, in the middle of the 1800s, they found that it accounted for almost all of the observed motion. Almost. There was a discrepancy, a tiny one. The orbit was rotating slightly faster than the theory said it should, by an amount so small it is hard to describe without sounding silly. About 43 seconds of arc per century. A second of arc is 1/3600th of a degree. Over 100 years, the orbit was drifting ahead of prediction by an angle roughly equal to the width of a small coin seen from a couple of kilometers away. That was the entire discrepancy, and it was real, and it was measured, and it would not go away. The obvious answer given the recent triumph with the outer planets, was another planet. If unexplained wobbles had revealed a new world once, why not again? The same French mathematician who had predicted the outer planet proposed exactly this: an unknown small planet orbiting between the Sun and the innermost world, and it was even given a name in advance, after the god of the forge. And astronomers looked for it. For decades, there were false alarms and claimed sightings and considerable excitement. And it was not there. It has never been there. It does not exist. So there it sat. 43 seconds of arc per century. One tiny stubborn number that the most successful theory in the history of science could not account for. Rest there a moment and hold that, because it is the hinge of this entire story. Everything else worked. Comets on schedule, a planet found with a pencil, the tides the shape of the Earth, the orbits of the moons of Jupiter, all of it perfect. And one small planet, closest to the Sun, drifting ahead of where it was supposed to be by an amount you would need a very good telescope and a century of patience to even notice. It is one of the recurring lessons of science, and it is worth carrying with you. When a theory is nearly perfect, the interesting thing is not the vast expanse of what it explains. It is the tiny corner where it fails, because that little error is not noise. It is the universe, quietly and politely, telling you that your beautiful picture is not quite the truth, and that something deeper is waiting underneath. Nobody knew that then. For half a century it was simply an annoyance, a loose thread, something to be tidied up eventually with a better measurement or a smarter correction. And then at the beginning of the last century, a young man in a patent office would sit down with an entirely different idea about what gravity is. Not a pull at all. Not a force reaching across empty space. Something else, something far stranger, and he would work it out over 10 years of enormous difficulty, and when he finally applied it to that one small planet, the answer would come out at exactly 43 seconds of arc per century. He said afterward that when he saw the number come out right, he was so excited that he had heart palpitations and felt as though something had snapped inside him. He knew in that moment that he was right about the universe. But that is tomorrow night. For now, let the story rest here, in the long golden confidence of the age when gravity was a solved problem, with the comets keeping their appointments and the planets found by arithmetic and one small stubborn discrepancy, 43 seconds of arc per century, ticking quietly away in the corner where nobody was really looking. So let your breathing slow, and let the plague year farmhouse, and the apple in the grass, and the cannon on the mountain, and the letter to Berlin all grow soft and dim and far away. It was all so long ago. They have all long since laid down their pens and gone to their rest, the difficult genius and his generous friend, and the mathematicians with their impossible calculations, having handed the puzzle on, as we all do, to the ones who came after. There is nothing here you need to carry tonight. It is only a story about people working out that the sky and the ground are the same place, told to carry you gently down into sleep. And the moon is up there right now, whether you can see it or not, falling toward you, as it has fallen every second of your life, and every second of every life before yours, and never arriving, and never will. It has been missing us for 4.5 billion years. It is very good at it. It will go on missing us tonight, quietly, while you sleep. Sleep now, warm and safe and held, on a solid world that is exactly where it should be. The story will still be here tomorrow night, with its ending and its curved space, and its number that came out right. And we have all the time in the world to follow it, gently, together, to the end. 43 seconds of arc per century. That was all that stood in the way. That is where we left the story last time. 200 years of triumph, a single law written on one line that had unified the heavens and the earth, explained the tides and the comets and the shape of the world, and let a man find an unseen planet with nothing but a pencil and some tiny errors in the motion of another. It was the most successful idea in the history of science, and to almost everyone it was simply the truth, finished and complete. And there were two small clouds on it. One was philosophical, a discomfort that had troubled the great man himself, about how the sun could possibly reach across 150 million kilometers of nothing at all and take hold of the earth. And the other was that stubborn little number, the tiny drift in the orbit of the innermost planet, that the theory could not account for, and that would not go away no matter how many times it was measured or how hard people searched for a hidden world to blame it on. Tonight, both clouds clear at once. Tonight we come to the second of the two great ideas in this story, and it is, I think, the most beautiful thing any human being has ever thought. It says that gravity is not a force at all, that nothing is pulling on anything, that the reason you are held to your bed tonight, and the reason the earth circles the sun, and the reason light bends, and the reason time runs slower in the valleys than on the hilltops, is all one thing, and it is not a pull but a shape. And then gently we will bring the whole long story home, from a stone dropped in the ancient world to the shape of space itself, and lay it down to rest, and ourselves with it. But before we begin, let me ask you one last time, and as softly as ever, if these quiet journeys through the great stories of our world have brought you a little peace across these nights, if they have helped you set down your days and drift off into rest, then please take just a moment to subscribe. It is one small tap, but it means the next of these will find its way to you when you need it, and it helps. More than you could know to keep these stories being made, for you and for all the others out there in the dark tonight, looking for a little rest. So if you would, subscribe and stay with me, night after night, as we wander on together through the great, slow stories of how our world came to be understood. And tell me, if you will, from wherever you are resting tonight, where you are listening from, and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there together, all of us drifting off beneath the same turning sky. And now, one last time, let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me to a small office in Switzerland at the beginning of the last century, where a young man with no academic position at all is about to have the happiest thought of his life. Let us begin with a man falling off a roof. In the early 1900s, there was a young man working as a clerk in a patent office in Bern. He had trained in physics and had not managed to get an academic post, and so he examined patent applications during the day and did theoretical physics in the evenings and in the gaps between applications, entirely outside the university system, with no laboratory, no colleagues to speak of, and no funding. In a single extraordinary year in his mid-20s, he published several papers that between them remade the foundations of physics. One of them established that light comes in discrete packets, which helped to found the entire physics of the very small. One of them proved the reality of atoms from the jittering of pollen grains in water. And one of them introduced the theory we now call special relativity, which showed that space and time are not the fixed and absolute backdrop everyone had assumed, but stretch and change depending on how you are moving. That last one had a problem baked into it, though, and he knew it. Special relativity worked beautifully for things moving steadily, but it did not include gravity at all. Worse, it seemed flatly incompatible with the old law of gravity, because the old law had the pull acting instantly across any distance, and the new theory said that nothing whatsoever can travel faster than light. The two could not both be right, so he set out to fix it, expecting it to take a few months. It took 10 years, and it nearly broke him. And I want to say something about those 10 years, because the popular picture of this man is of effortless genius, of answers arriving whole in flashes of inspiration, and the reality was almost the opposite. It was a decade of grinding, frustrating, often humiliating labor. The physics was one thing, the mathematics was another, and it very nearly defeated him. To describe curved space properly, he needed a branch of geometry that he had never learned and that most physicists of the day had never heard of, and he had to go to a friend, a mathematician, and effectively be taught it from the beginning as a man in his 30s who was already famous. He wrote to that friend at one point begging for help and saying that he had never in his life tormented himself so much over anything. He went down blind alleys and stayed in them for years. He published versions that were wrong and had to withdraw them. At one stage he convinced himself, through a subtly flawed argument, that the theory could not work in the way he wanted, and he abandoned the correct path for nearly 3 years before finding his way back to it. His health suffered badly. His marriage fell apart during those years. He worked through a war that cut him off from many of his colleagues abroad. And at the very end, in the final weeks, he was racing. One of the greatest mathematicians alive had become interested in the problem and was closing in on the same equations from a different direction. And there were a few tense weeks in which it was not at all clear who would get there first. He finished in November of 1915, presenting the completed theory over 4 consecutive weekly lectures, each one closer than the last, arriving at the final form in the 4th. 10 years for 4 lectures. That is what it actually costs, not a flash. A decade of being wrong in increasingly interesting ways. And it began, he said afterward, with the happiest thought of his life. He was sitting in his chair at the patent office thinking when it came to him. If a person falls freely, he will not feel his own weight. That is it. That is the whole thought. It sounds like nothing. It sounds like an observation a child might make. And out of it came the entire modern understanding of gravity, space, and time. So let us sit with it gently, because it repays every second you give it. Imagine a man on a roof who slips and falls. In the moments while he is falling, before the ground arrives, what does he feel? He does not feel heavy. Nothing is pressing on him. There is no floor pushing up against his feet, no chair against his back. If he had a stone in his pocket and let it go, it would not drop away from him. It would hang there beside him, falling exactly as fast as he is falling, apparently weightless. Inside that fall, gravity has vanished, not weakened, vanished. Everything inside that falling frame behaves precisely as if there were no gravity at all. And now turn it around, which is the other half of the thought. Imagine you wake up in a sealed room with no windows and you feel yourself pressed against the floor. Are you in a room sitting still on the surface of a planet? Or are you in a spacecraft, far out in empty space, with the engines firing steadily, accelerating you upward, so that the floor is pushing against you? And the answer is that there is no experiment you could perform inside that room that would tell you. None. Drop something, and it falls to the floor in either case, at the same rate, whatever it weighs. Weigh yourself, watch a pendulum, throw a ball, shine a torch. Every result is identical. Gravity and acceleration are not merely similar. They are, as far as anything inside that room can ever determine, exactly the same thing. And that innocent-looking statement has a consequence that he spotted almost at once, and it is where the whole theory begins to open out. Imagine you are in that sealed room, out in space, engines firing, accelerating steadily upward, and you shine a torch horizontally from one wall to the other. The light travels across the room at a fixed speed, taking a certain very small amount of time to cross. But during that time, the room has accelerated upward, so by the moment the light reaches the far wall, the wall has moved up a little, which means the light hits the far wall slightly lower than where it left. From inside the room, the beam of light has curved downward. Now, if gravity and acceleration are truly indistinguishable, then the same thing must happen in a room sitting still on a planet. Light must bend downward in a gravitational field. It must fall, like everything else, and light has no weight. Under the old picture, there is no obvious reason at all why gravity should have any effect on it. But if gravity and acceleration are the same thing, it has no choice. That is a real, testable, unavoidable prediction, and it came straight out of a thought about a man falling off a roof. He had it long before he had the full theory, and it would eventually be what made him famous across the entire world. Rest there a moment, because we have just quietly solved the mystery from our first night. Remember that strange coincidence, the one that had sat unexplained for 300 years. The property that determines how hard gravity pulls on an object and the property that determines how hard it is to accelerate are always identical in every material. To every decimal place anyone can measure. Nobody knew why, now you know why. They are the same number because they are the same thing. Gravity is not something separate that happens to grip objects in proportion to their resistance. Gravity is indistinguishable from acceleration. And that is also why everything falls at the same rate, which the Italian had discovered with his bronze balls 3 centuries earlier without ever knowing what it meant. It is not that gravity is politely careful to pull on everything just right. It is that falling is not being pulled at all. 2 mysteries, 300 years old, dissolved in a single sentence. That is what it feels like when somebody finds the right idea. But if nothing is pulling, then what is happening? Why does the apple move at all? Here is the answer, and it took him 10 years of the hardest work of his life to make precise, so we will take it gently. The old picture said that space is a fixed, empty stage, the same everywhere, and time is a universal clock ticking identically for everyone, and objects move around inside that unchanging arena while forces push and pull them. The new picture says there is no fixed stage. Space and time are woven together into a single flexible fabric, and that fabric is not a backdrop but a participant. It can stretch, it can curve, and matter and energy bend it. And here is the crucial part, the sentence that contains the whole theory. Everything always moves in the straightest possible line through that fabric, always. A thrown ball, a planet, a beam of light, all of them are simply going straight ahead. But when the fabric itself is curved, the straightest available path is a curve. Think of two people setting off from the equator, walking due north on perfectly parallel paths, each walking as straight as they possibly can, never turning. As they walk, they will find themselves getting closer together, and if they keep going, they will eventually meet at the pole. Now, nothing pulled them together. Neither of them turned. Neither of them felt any force. They both walked in the straightest line available to them. They converged because the surface they were walking on is curved. That is gravity. That is all of it. The Earth is not being pulled around the sun. The Earth is going straight ahead, as straight as anything can go through a region of space and time that the sun has bent. And the straightest path through that bent region happens to loop around and come back to where it started. And the apple in the garden? The apple is not being pulled down. The apple is at rest in space, but it is still traveling forward through time, as everything does. And the Earth's mass has curved the fabric in such a way that a path going straight forward through time also bends downward through space. The apple simply goes straight, and straight near the Earth means down. That last point is subtle, and it is worth one more moment because it clears up something that troubles a lot of people about the usual picture. You have probably seen the illustration of gravity as a heavy ball sitting on a stretched rubber sheet, with a marble rolling around the dip. It is a useful picture, and I have used it myself in an earlier series. But it has an obvious flaw, which is that the marble only rolls into the dip, because there is real gravity underneath the whole demonstration, pulling it down toward the floor. The picture explains gravity using gravity. The real answer avoids that, and it is this. The curving is not only of space, it is of time as well. And it turns out that for anything moving at ordinary everyday speeds, it is mostly the curving of time that does the work. Here is what that means. You are right now moving through time at a considerable rate, and hardly moving through space at all. So most of your path through the fabric is pointing in the time direction. And the Earth beneath you has bent the fabric so that time runs a fraction more slowly nearer the ground. Which means that your straight path forward through time is very slightly tilted toward the region where time runs slower, which is downward. So the reason the apple falls is, in a real sense, that time runs a tiny bit slower at the grass than at the branch. And the apple, going straight ahead through time as everything must, drifts toward the slower part. That is not an analogy. That is close to the literal content of the theory. Falling is what going straight forward through time looks like when time itself has been bent. Rest there a moment and let the strangeness of it settle over you gently, because it is worth sitting with. Nothing in this room is being pulled on. Not the cup on the table, not your body in the bed. The floor is pushing up against you, and you can feel that, and that push is real. But there is nothing at all pulling you down. You are simply trying to follow the straightest path through a region of space-time that this whole enormous planet has gently curved, and the floor is in the way. That is why the falling man feels nothing. He is not being pulled. Left alone, he is doing the most natural thing in the universe, going straight ahead through curved geometry. The strange, unnatural, forced condition is the one you are in right now, held still by a floor or a bed that keeps shoving you off your natural path. Weight is not the feeling of being pulled. Weight is the feeling of being stopped. Now, a theory this strange has to earn its place, and it does that by making predictions that the old theory does not make. And it made 3. The first was that little planet. When he finally had the equations working, he applied them to the innermost planet and calculated how much extra its orbit should drift, over and above what the old law predicted, not adjusting anything to fit, not inserting a new planet or a fudge. Just the raw output of the new theory, 43 seconds of arc per century. Exactly the discrepancy. Exactly the number that had sat there unexplained for half a century. He wrote later that he was beside himself with excitement for days, that he had heart palpitations, that he felt something snap inside him. He had not set out to explain that number. It fell out of the mathematics on its own. And in that moment, alone with a piece of paper, he knew that his picture of the universe was correct. Rest a moment on that image, because it is one of the great private moments in the history of science. No audience, no apparatus. A man at a desk, doing a calculation and watching a number come out of it that matched something astronomers had been unable to explain for 50 years. He knew before anybody else in the world knew that space and time bend. The second prediction was about light. Under the new picture, light must follow the curve of the fabric like everything else, which means a beam of light passing close to a massive object should be deflected. And the old theory made a prediction here too, of sorts, but the new theory predicted almost exactly twice as much bending. So here was a clean test with two different answers. How do you test it? You need a very massive object, and you need to see light passing close by it. And the only sufficiently massive object nearby is the sun. So you need to observe stars whose light passes right by the edge of the sun and check whether their apparent positions have shifted, which is impossible because the sun is blindingly bright and you cannot see stars next to it. Except during a total eclipse, so in 1919, just months after the end of a catastrophic war, expeditions from Britain sailed to an island off West Africa and to northern Brazil to photograph a total eclipse and measure the positions of the stars around the darkened sun. There is something quite moving in that, incidentally. British astronomers crossing the world at considerable expense and difficulty to test the theory of a German physicist, so soon after their two countries had spent 4 years destroying each other. The organizer of the expeditions was a man who had refused to fight on grounds of conscience and who argued that science should stand above nations. The weather was poor. One site was clouded for most of the eclipse, but they got their plates and they measured them and the stars had moved. By close to the amount the new theory predicted, and roughly double what the old one allowed. The details of that expedition are rather wonderful, if you like a story about people struggling with equipment. At the African site, the morning of the eclipse brought heavy rain, and the sky was completely covered, and the astronomers stood there watching the clouds and knowing that they had traveled halfway around the world and waited months for a window of a few minutes that they were about to lose entirely. The rain stopped only shortly before totality. The sun appeared through gaps in the cloud. They took their photographs anyway, exposing plate after plate on faith, mostly through cloud, and of the 16 plates they took, only 2 turned out to be usable. 2 plates. After crossing an ocean and waiting through the rain and a war and years of preparation, and those 2 plates were enough. The Brazilian expedition had better weather, but ran into a different problem, a piece of equipment distorted by the heat, which ruined their main set of images and left them relying on a backup instrument they had almost not bothered to bring. So, the confirmation of the greatest theory of the century came down to a handful of salvaged photographs from 2 expeditions that had both gone partly wrong. That is very often what real evidence looks like. Not clean, not decisive on the day, argued over afterward for years, and right. The announcement was made in London that November, and the reaction was extraordinary. It made the front pages of newspapers around the world. A patent clerk who had been nobody 15 years earlier became, essentially overnight, the most famous scientist alive, and one of the most famous people on Earth, a status he never lost and never much enjoyed. And the third prediction was about time. We touched on this in an earlier series, but it belongs here properly because it is the strangest consequence of all. If space and time are a single fabric, and mass bends that fabric, then mass affects time as well as space. And it does. Time runs more slowly where gravity is stronger, not appears to. Does. A clock at sea level ticks more slowly than an identical clock on a mountain. A person who lives their whole life on the ground floor ages, very slightly, less than a person who lives on the top floor. The effect is tiny at the scale of a house, a matter of billionths of a second over a lifetime, but it is real, and it has been measured, with clocks precise enough to detect the difference over a single flight of stairs. And here is the part that makes it wonderfully concrete. Your satellite navigation depends on it. The satellites that tell your phone where you are carry atomic clocks, and they sit far above the Earth where gravity is weaker, so their clocks run faster than clocks on the ground by about 45 millionths of a second a day. Their speed pulls the other way and slows them by about 7 millionths. Net effect, they gain about 38 millionths of a second every day. That sounds like nothing. It is not nothing. Light travels about 300,000 kilometers in a second, and these systems work by timing signals. If that correction were not applied, positions would drift by something like 10 kilometers every day, and the whole system would be useless within minutes. So every navigation system on Earth is quietly running a correction, all day and all night, for the fact that time itself runs at different rates at different heights. That strange, abstract, 100-year-old idea about the shape of space-time is in your pocket, working right now. Rest a moment there because I find that quietly delightful. The theory that says gravity is the bending of space and time is not a beautiful abstraction locked in a textbook. It is a piece of working infrastructure. Every time a delivery driver finds an address, or a ship makes port, or a phone shows a little blue dot, curved space-time is being accounted for correctly to the microsecond. And the theory has kept on being right, over and over, for more than a century, in every test anyone has devised. It predicted that space itself could ripple, and 100 years later, two enormous instruments felt those ripples arrive from two black holes colliding a billion light-years away. It predicted that light passing a massive galaxy would be bent enough to form arcs and rings, and multiple images of things behind it, and telescopes see exactly that, everywhere, and astronomers now use it as a tool to weigh galaxies. It predicted that space and time could curve so severely that a region would seal itself off entirely, and we photographed the shadow of one a few years ago. Every prediction, every time, for over 100 years. And yet it is not the end of the story, and I want to be honest with you about that before we close, because the honesty is the loveliest part. There are two enormous unanswered questions still sitting in the middle of all this, and they are as open tonight as they have ever been. The first is that when we look at the universe and add up the gravity, the numbers do not work. Galaxies spin far too fast for the amount of matter we can see in them. They should fly apart. Something is holding them together, something with mass that gives off no light of any kind. There appears to be a great deal more of it than there is of ordinary matter, several times more, and we have no idea what it is. We call it dark matter, which is a name for our ignorance rather than an explanation. The way that was discovered is a story worth a moment on its own. In the 1970s, an astronomer set out to do something that seemed almost too routine to bother with. She measured how fast the stars in nearby galaxies orbit their centers. The expected answer was plain physics. In our own solar system, the inner planets move quickly, and the outer ones move slowly because gravity weakens with distance. The same should be true of a galaxy. The stars far out at the edge, where there is very little visible matter, and the center is a long way off, should be dawdling along. They were not. They were moving just as fast as the stars near the middle, all the way out, in galaxy after galaxy, which is impossible unless there is a great deal of unseen mass out there, extending far beyond the visible edge, holding those outer stars in place. The galaxies we see are, apparently, only the glowing centers of something much larger and completely invisible. She was not the first to suspect something like this, but her measurements were careful and consistent and impossible to argue away, and they were dismissed or ignored for years before the field came around. She never received the highest prize in physics for it, which many people consider one of the plainer injustices in the recent history of science. She died in 2016, with the puzzle she had uncovered still entirely unsolved, and on the largest scales, something even stranger. The expansion of the universe, which everybody expected gravity to be gradually slowing down, is instead speeding up. Something is pushing space apart, and by the accounting it makes up the majority of everything there is, and we understand it even less. We call that dark energy, which is again a label rather than an answer, which means that our best current picture says the overwhelming majority of what fills the universe is stuff we cannot see and cannot identify. Everything we know, every star and planet and person and atom, is a small fraction of the total. That is where we actually stand. And the second open question is deeper. We have two magnificent theories. One describes gravity and the shape of space-time at the largest scales, and it is essentially perfect. The other describes matter and energy at the smallest scales, and it is also essentially perfect. And they cannot both be true because they contradict each other at the edges. Nobody has managed to join them, though some of the finest minds alive have spent their entire careers trying. It has been open for a century now, almost everywhere. This does not matter because gravity is negligible where things are tiny, and things are enormous where gravity is strong. The two theories rarely have to meet, but there are places where they must. The center of a black hole, the first instant of the universe. And there our understanding simply stops. Rest there a moment and let that be a comfort rather than a frustration, because I think it is. It means the story is not over. It means that the thing we have been following for 3 nights, from a stone dropped in an ancient garden to the curvature of space-time, is still going. There is another chapter, and nobody has written it, and somebody eventually will. And so, we come to the end. Look back over the whole of it, if you will, as you drift. 2,500 years ago, a philosopher looked at a falling stone and said that it was going home to its natural place, and the world believed him for 2,000 years. A man in Italy rolled a bronze ball down a plank 100 times and found that everything falls together and was made to renounce what he knew. A difficult young man in a plague year looked at an apple and then at the moon and asked why one falls and the other does not, and answered that both of them do. And a clerk in a patent office sitting in his chair thought about a man falling off a roof and realized that gravity is not a force at all, but the shape of everything. 4 ideas across 2.5 millennia, each one built on the last, each one arrived at by somebody simply paying very close attention to something that everybody else had walked past. And notice that not one of them needed to leave home to find it. No expeditions, no great instruments until the very end. The whole of it came out of ordinary things. A stone, a ball on a plank, an apple in the grass, a man imagining himself falling. The universe was showing us all of this constantly, everywhere in every dropped cup, for 100,000 years, waiting for somebody to look properly. So let it rest now, all of it. Let the whole long story lie down at last and be at peace. Let the ancient philosopher rest, with his 4 elements and his perfect crystal spheres. Let the old man in Italy rest, dictating his final book to his students in a room he was not allowed to leave, going blind still right. Let the difficult genius in the farmhouse rest and the generous friend who coaxed the book out of him and paid for the printing. Let the mathematicians rest who found a planet with a pencil. Let the clerk in the patent office rest who sat in his chair and thought about falling. They looked at the most ordinary thing in the world and would not stop asking about it, and between them they worked out the shape of the universe, and every one of them has long since laid down their work and gone into the quiet, having handed the question on, as we all do, to whoever comes next. And out there right now while you rest, all of it is going on exactly as it always has. The Earth is going straight ahead through curved space, as it has every second for 4.5 billion years, and coming back around to where it started, and doing it again. The moon is falling toward you and missing as it has always missed. The tides are rising somewhere on some shore in the dark. The galaxies are turning, slowly, unimaginably far away, each one held together by the same thing that is holding you in your bed. None of it needs your attention tonight. It has been running for 13 billion years without supervision. It will keep running while you sleep. So let your breathing slow one last time, and let the ramps and the apples and the eclipses and the curving of space all grow soft and dim and very far away. The story is told, or as much of it as anyone has yet. There is more to come, and someone will find it, and it will not be tonight, and it does not need to be you. Let the whole sky settle now and slow and quieten. Let the planets go round without being watched. Let the moon go on falling and missing, as it has for 4.5 billion years patiently, in the dark above your roof. Let the galaxies turn, so far away that the light arriving from them tonight set out before there was anything here to see it. None of it is in any hurry. None of it ever has been. And let all of them rest, the ones who worked this out. The philosopher with his elements, the old man dictating in his locked house, the difficult young genius in the plague year garden, the generous friend who paid for the book, the clerk who sat in his chair and imagined falling. They are all long gone now, every one of them, and they left us a universe we can understand, which is about the largest gift anyone can leave. You are held. That is the last thought I will leave you with, and it is not a metaphor. Of every force in the universe, gravity is the one that never lets go and never has and never will. It has held you every second of your life, from before you were born. It is holding you now, in your bed, quietly, along with the air in the room and the roof over your head and the whole vast patient world beneath you. It asks nothing. It simply holds. And that is what it has always been doing, under everything, all along. Holding the water in the oceans, holding the air against the ground so that there is something to breathe, holding this world in its long, steady circle at exactly the right distance from its star for 4.5 billion years, without once wavering, so that there could be mornings and evenings and seasons and life and eventually people, and eventually you lying here tonight in the warm. It has been holding you all your life, and you have never had to think about it once. You do not have to think about it now. You can let go completely, it will not. Sleep now, warm and safe and held, on a solid world in a quiet corner of space, going straight ahead through the dark. And it will still be turning gently exactly as it should when the morning comes.